Okay.
Okay, why don't you get started?
Okay. Hello, everybody. I'm Elliot, and today we're going to be looking at the world through some BPS states. So, my original purpose of this was to try to sort of what's it called? To show a philosophy of the world, a philosophy that's been like kind of prevalent in recent applications of physics and mathematics, which is like the seeing BPS states everywhere you look, that sort of thing. So I'm going to try something fun, but you know we're in pleasant company here, so it's okay if I make some people angry. I'm going to start from a purposefully inflammatory stance, which is one that I don't even believe, but I'm going to aim to try to argue for that point anyways. And we'll see how it goes. So if I start like lying or saying something really wrong, then call me out on it, please. But let's start with a fact, 100% true, nothing fake about this at all. It's just a fact, which is that BPS states are the primary means that supersymmetry influences modern mathematics, and supersymmetry is like the most influential part of physics in general. So that's what I'm going to try to convince you of, even though I don't believe it myself. So what I'm planning to do for the couple of days. So today, I wanted to go in some detail about the first time that BPS states are actually used in this means, and it's a very good illustration of the sort of stuff you can do with BPS states, which is the Seiberg-Witten solution. This is something we've been kind of dancing around for a while. So I'm going to go. I think it deserves its due justice. So I'm going to maybe spend more time on it than is warranted. And then I wanted to get to something about like a overall kind of ambitious philosophy that I tried to come up with, but I don't know if I really had time. We'll see if we get there today or not. And then next week, I want to say how like everything else we've been doing this semester is secretly been BPS states all along. So just sort of connecting it to all of the other threads we've been talking about, Donaldson invariance, Seiberg-Witten invariance, all that sort of stuff. So I haven't done any of this yet, but I'm sure they are BPS states. I'll just figure it out before next week. So enough of the preamble. Let's get started with the Seiberg-Witten solution. So the Seiberg-Witten solution is an exact low energy effective field theory for n equal to supersymmetric Yang-Mills with gauge group SU2. So just to remind you a bit of stuff that we talked about before, n equal to supersymmetry is really, really nice because the actions you get are very limited. In fact, they're all controlled by a single holomorphic function called a prepotential. It's a function acting on this chiral vector multuplet, n equal to multuplet, which sort of holds all of the n equal to fields together into one thing. This holomorphic function is called the prepotential. And the high energy theory, the one that we're starting with, is just a very simple F equals Z squared. It's a free theory. It's Yang-Mills, supersymmetric Yang-Mills for SU2. And we want to see what happens when we take that theory and step really, really far back, kind of cross our eyes a little bit and see what sort of emergent dynamics emerge. So that's called the low energy theory. And well, what form could this have? Well, if you try to do perturbation theory, you can find that because of general nonsense about supersymmetry, you get a one loop exact part. In other words, like all you need to do, I want to reiterate, all you need to do is find this holomorphic function. And you already know what it looks like perturbatively. It's just this, Z squared ln Z. It's like this is like the beta function or something. But the issue is, we get contributions from instantons. Instantons are these states that are not topologically connected to the other things. And in quantum field theory, we need to add up over all of the states. Because the instantons are often their own little corner of moduli space, we can't reach them through our perturbative methods, which means that the majority of tools in quantum field theory are of no use for trying to calculate these exact things, right? So this actually takes the form of a bunch of quantum corrections yeah, where, you know, you can think about it as these like coefficients. So if you wanted to go through this like directly, I think this is where stuff like Nekrasov's partition function comes in. It relates to these coefficients in some way, like organizes them into a power series maybe. But we're not going to do that. Instead, we're going to take a totally different, an indirect route, which is championed by Seiberg and Witten in 1994, turning back the clock a few decades. We're going to figure out what the prepotential is indirectly, using a bunch of different physical intuitions and facts about n equal to supersymmetry and stuff like that. And in particular, our main tool is going to be BPS states. BPS states are going to tell us how to look into the geometry underlying this supersymmetric field theory, and thus let us, you know, deduce stuff from it. So there's a bunch of steps to this. So I tried my best to like condense it down into like as much of a logical progression as I could. And we're looking at this from the BPS framework. So let's start in a natural case, which is try to find the BPS states in the free theory, the theory that we're starting with, right? So this is essentially going to be a review of what I talked about like a month ago. But you know, it's a month ago. People probably don't remember, and this is important stuff for what I'm going to be talking about later. So I'm going to go through it. So just to remind you, this chiral multuplet in n equal 2 is like this big container holding a bunch of different fields. You can expand it out into like these n equal 1 things, where you get a vector multuplet as one part and a chiral multuplet as another. I mean, these are very scary names, but here's how you should think of them. They have fermion fields. We're not going to worry about the fermions today, but we're just going to integrate them out at some point later. We're mostly going to be worried about the bosonic fields. And then this vector part with this little mu index, this is going to be essentially the gauge field. And the terms involving this vector part are going to be the couplings to the gauge field. While the chiral multuplet, the thing we care about, is going to be the scalar field, this adjoint valued scalar field. That's the Higgs field. And then there's also a couple auxiliary fields that we still don't care about because, again, we integrate those out. So we can represent like this form of the Lagrangian is very nice for showing how simple it is, but it isn't particularly useful for doing anything. To do stuff with it, we need to expand out into its two component parts. Right. So this is just an exercise in n equal 2 stuff, but basically the first part has to do with the chiral superfield, and it's the derivative of f multiplied by, you know, the conjugate of the field, suitably interpreted. So this is like a potential term. That's sort of what this contains. I should say I'm using just prime here because we're in a rank 1 Lie algebra. So we're only dealing with one sets of these fields. So it really is just a single holomorphic function. In higher rank cases, we have to do with holomorphic functions with multiple components, which is something I'll return back to periodically just so that you can see what it looks like, but it's not what we're going to be focusing on. So the other part is this part involving the vector multuplets. It involves a second derivative and it couples to, you know, the vector multuplet squared essentially. And this is where all of the Yang-Mills theory comes in and all of the interactions come in. So this is kind of where most of our heart's going to lie. And in the specific case of, you know, the free theory, Z squared, we have this very nice expansion of the Lagrangian where we can recognize what all of these terms really mean. So sort of, you know, I'm being rather schematic about this, but we have a Yang-Mills term. We have a Higgs field that is coupled to the gauge field in a minimal way. And we have this potential term, which has to do with the commutator of the Higgs field with itself. So this together makes up the Yang-Mills Higgs Lagrangian. And this is something that I talked about in some detail last week, but it's a theory where you get monopoles. That's what comes out of this. So that should give you some hint about why Seiberg and Witten are talking about stuff like monopole condensation in their paper. It ultimately boils down to the fact that, you know, the Lagrangian you get from n equal 2 looks very similar to the Lagrangian used to solve for monopoles. And on top of that, we have the stuff involving fermions, the supersymmetry terms. Both of these fermions are free. I changed them, no, I didn't. And then there's a coupling of the scalar field, but again, we're going to kind of ignore these today. So as I was saying, in the Yang-Mills-Higgs theory, the classical solutions of it are going to be these static states, and they're going to be monopoles. And in particular, at low energy, this potential term has a spontaneous symmetry breaking effect, whereby essentially it forces, at low energy, this term forces the Higgs field to be constant everywhere. This term forces it to be non-zero. And when the Higgs field is non-zero, its coupling with Yang-Mills through this term enforces that the Yang-Mills field sort of plays nice with the Higgs field. It preserves the Higgs field. And what that ends up doing is it breaks the symmetry from this full SU2 to a U1 symmetry. You know, as you go in really low energies, as you go off to infinity, this is what happens. So this is going to drastically simplify the theory and make it a lot easier to analyze if you're a mathematician. So in particular, we can get BPS stuff. Like in the static case, we can actually split the curvature into like an electric and magnetic part. That's the consequence of looking at time-independent solutions. And we can look at the charges of states, and it corresponds to essentially the amount of electric flux and magnetic flux going out of at infinity. So these are going to be quantized things. They're going to be topological quantities because they measure, effectively, these are the Chern classes of some vector bundle at infinity, and where this is like the integrating the curvature form, but basically they're going to be topological invariants and they're going to be integers. So the question, so these integers sort of measure how much the field twists around at infinity. How much the U1 field that you're breaking down to is going to twist around. And if the field is twisted, then you know one thing for sure, it can't have zero energy, where energy is sort of like a measure of global twisting over the whole modulus, over the whole R3, if you want to call it that. You can't have global twisting. Sorry, you can't have it be constant. So there has to be some twisting, there has to be some energy. How much? That's what's given by the BPS bound. It gives you a bound on the energy in terms of the topological charges at infinity. Okay, let's do it like this. On the other hand, as I talked about last time, again, quantum mechanically, BPS states arise in a different way as representations of the supersymmetry algebra, where basically we're including a central charge in this algebra, which is a statement about, you know, the commutators of the two supersymmetry charges. And we end up getting that the mass of a state is going to be greater than or equal to the norm of the central charge. And this tells us a lot of really nice things. In particular, when my mass is equal to the central charge, what I call a BPS state, because it saturates the BPS bound, that means that I'm actually going to be annihilated by half of the supersymmetry. So it's like a partially supersymmetric state, which is nice because it means the representation that it lives in, remember, we're talking about representations of the supersymmetry algebra, it's going to be a smaller dimension, which is really useful because, for example, if I have a single state, a single BPS state, say it's 4-dimensional, well, if I increase the mass above Z, then it's going to be not a BPS state, and the representation has to be 16-dimensional. But I can never just deform my theory and get 12 dimensions out of nowhere, right? So this dimensionality constant gives a sort of deformation invariance to how these BPS states work, which makes them really useful for probing stuff like these non-perturbative dynamics, which is what we're going to see later. So last time, the main punchline I gave was that these two are actually secretly the same. This is adapted from this classical Olive-Witten paper back in the 70s even. And the way we see this is by manifesting my supersymmetry as operators on as differential operators on space. So this is called the superspace formalism. And in particular, now these are differential operators. When I'm in my free case, specifically when I'm in this case where the Lagrangian is just, f is just z squared, then what I can do is I can use Noether's theorem, and I can tease out of that formulas for the conserved charges associated with these symmetries. And in fact, they're very familiar, luckily. So the z, the central charge, is actually going to give you the integral over infinity of the electric field, and then the integral over infinity of the magnetic field, with this complex coupling constant in between. And remember from this definition up here, this is just going to be the charges with this coupling constant. While the mass is going to end up being essentially the energy density, again, the one we found up here for classical BPS states. So together, it means that these are actually the same. Like a BPS monopole, when represented quantum mechanically, gives you a BPS state. It gives you a state with the BPS bound, right? So we get this equivalence between the central charge and the charges of the monopoles. I just wrote it as a proportionality, but this is basically the crux of why we care about this. We're actually relating the central charge to these monopole charges. So this is basically where the review stops. So I'm gonna stop to take a breath if anybody has any questions. Okay, wonderful, in case there's nothing in chat. So, okay, why do we care about this? Well, this actually tells us something interesting about the quantum properties of the central charge, which is that we know that these are quantized. These numbers are quantized, which means that they form a sort of lattice, a lattice of possible charges that these states can have. Because again, these are just integers. It's isomorphic to the integers, right? And then the central charge is essentially a function that takes your two integers in and throws out a complex number. So it's basically a way of realizing the lattice as a sublattice of the complex numbers. So for example, in this case where we have this parameter tau, this ends up giving us a charge lattice where the lattice parameter is this tau again. So these are the lattice of possible charges. And we have more structure because of a Dirac quantization condition, which essentially gives you a symplectic pairing on this lattice. So we're going to get a symplectic structure on top of this lattice structure. So this is the case for free theories. This is what happens in ad infinity in this trivia, in the theory that we're trying to pull back to low energy approximation. Which brings us to the goal of actually extending this to the non-free theories. So the classical, so we're going to be, I think Se-Hong talked about this, but basically the moduli space of solutions to these things, basically that's the formalism we're going to have to deal with. So the classical moduli space is given by the moduli space of classical solutions, which extremize the Yang-Mills energy, will enforce that d of the Higgs field is 0, essentially that the Higgs field is constant. So they're parameterized by the value of the Higgs field, or more accurately, I guess, the value of the gauge invariant stuff that you can tease out of the Higgs field. Remember, this is a Lie algebra, so we're just going to take the Casimir invariant of it, one of its invariant polynomials. Let's call it U. So the parameter space is going to be the U plane. In quantum mechanics, general nonsense about n = 2 says that these vacuum states are not going to be lifted. They're going to stay. Yeah, they're going to stay. It's going to stay the same moduli space, but now it's going to be parameterized by the vacuum expectation value of this operator instead of just the operator itself. But the point is, we have a quantum moduli space whose space is C. Now, The SU2 theory we're considering has a very physically useful property called asymptotic freedom, which basically says, as I look at really, really high energies, which in this case is equivalent to looking at very, very large values of the Higgs field, essentially going really far out in the U plane, as I look in this limit, I'm going to get a free theory, right? It's going to be described by this, where is it? Oh, it's just a z-squared function. And there it is. It's going to be described by the z-squared function. And in particular, this theory has already been broken down to U1. So it's just a free U1 theory. And we know how to deal with those already. And the question is, what if I take this theory and sort of yank it back and pull it back to try to some finite parameter of U, where it's no longer a free theory? How can we do this? And the insight is to use the BPS states, right? Now, this is actually a kind of interesting point because I mean, I might be wrong about this, but from what I understand, when I'm in this finite zone, when my theory is no longer free, then that breaks the way that we constructed these quantized charges, because we used specifically this Lagrangian, and we used we used it to construct the conserved charges. In a non-free theory, then I think you're going to lose that interpretation. You're going to lose this necessary topological quantization, and your interpretation in terms of charges. But here's the magic of BPS states, because roughly speaking, they don't deform, which interpreted correctly, that says that this formula of Z in terms of these charges is going to have the same form everywhere on moduli space. Even though the other particles might do all sorts of nonsense and break away from the lattice, the BPS states will still form this nice charge lattice, this nice integral charge lattice. And in particular, it is indeed a lattice. Like, these states do not just all move around willy-nilly on their own, but the fact that it's a lattice uses another physical input. So this uses the notion of electric magnetic duality, which is an exact quantum symmetry of the theory that you can see by essentially just rewriting the fields in your Lagrangian. So I'm not gonna, I don't think I'm gonna go into this in too much detail because I feel like we've seen it before. I don't really remember though. But basically the idea is we're gonna try to form a dual theory where we replace electric and magnetic charges. We're gonna do that by replacing the curvature with its Hodge star as the sort of fundamental field of the theory. And we plug it in and we have to impose some external facts like the Bianchi identity, because this is no longer curvature form. This is something we have to say. And when we do that, we end up getting a different action. And that action will be the same except for this, this complex coupling constant, of which it will be sent to -1 over its inverse. And this is along with another symmetry of the theory where the real part of the coupling constant is periodic. So you already have this symmetry of just shifting things to the side. So together, we can look at this in terms of the lattice. Remember, this lattice is sort of generated by this tau parameter. And these operations you do on the tau parameter correspond to operations on the lattice. So I'm starting here, for instance, in my tau plus 1, what I'm doing is I'm shearing the lattice. I'm sending this top state. Yeah, I'm shearing it over by 1. I'm changing, so I get a lattice that looks the same, but with a different basis. Likewise, this -1 over tau is sort of rotating the lattice by 90 degrees. So this is an exact symmetry of the theory. And in particular, it means that our charges have to be, our possible charges have to be acted on by the lattice. And this lattice will have to be acted on by SL2Z. And this SL2Z will turn those single charges into a whole lattice. So essentially, here is the, the bottom line is that we use the fact that we have BPS states to pull back our lattice at infinity, which we know exists, into a set of states at finite time. And we use electric magnetic duality to ensure that this is indeed a lattice. So in fact, these two properties together mean that over every point in our moduli space, we're going to get a lattice over this moduli space, over this Coulomb branch, and it's going to have a nice symplectic form. So this is sort of the geometry of the Coulomb branch. This is where the geometry comes from mostly, these physical techniques. Both of these are pretty physically motivated, and I don't even know if they're mathematically formalized ideas, but basically they tell you that you should have this structure over the Coulomb branch, where the Coulomb branch parameterizes U1 theories, and the charges of those theories with respect to the BPS states, they are lattices. Okay, take a breath again. Okay, so that's half of the battle. Question is, what did Lee's lattices do? Oh, right, I should mention, did I mention this? Yeah, I did not mention this yet. So basically what the point of view I'm taking right now is that we're trying to use these physical ideas to create some sort of interesting geometry on the space. And later we're going to see that this geometry actually lets us solve the theory. But first we're building up what structures the space has. So we saw that it has these nice lattices. Now we want to constrain how these lattices behave as a function of U. And this requires a cute little trick. So this is going to probe sort of the geometry of this moduli space. Okay, so our lattices are parameterized by the expectation value, our moduli space is parameterized by the expectation value of the Higgs field. And we looked at the gauge invariant quantity U, but if we look at the 2x2 form of the Higgs field, it's going to be this real number A, complex A, which is going to square to U. This is just like, it's very confusing how these two things relate to each other. But basically, we have this A, keeping this in our back pocket. The trick is that A has a different value on every point on the moduli space. In fact, because of this, it actually has two values, but that's beside the point. Every point is distinguished by its value of A. So we can pretend that A isn't like an abstract field. We can instead say that A is actually a field valued in this moduli space. It's a sigma model. It's a map from R4, like my physical space, to the moduli space of vacua. And we can see this physically in a different sense. So imagine that this is my UV theory, and my A is like a scalar function. It's this big wobbly thing, right? So this is my A in the high energy limit. And then I sort of take a very, I zoom out a lot. I expand everything, and I go to the IR limit. So in that case, we can take this little part of A, and we're scaling it up. We're scaling the metric to be this huge section. And we see that A now, even though it was all squiggly before, now it's like roughly flat. And to good approximation in the actual IR limit, we can say that this A is locally constant. And then the local field configurations are going to vary much faster than A. So we can treat it as if A is constant in this space. And then the possible field configurations are just going to be, in this low energy limit, they're going to be the zero energy configurations locally. So locally, it's going to be in a vacuum state. So this A, it sort of picks out, we can think of this field as sort of picking out a vacuum state of this moduli of vacua at every point in R. So we're thinking of A in this IR limit as a sigma model to this moduli space. It sounds real. I think it sounds kind of fancy, but this is something you like do all the time without even realizing it, I feel. Anyway, this is cool because we can interpret the Lagrangian now in terms of a metric on our moduli space, in terms of our sigma model. So basically the kinetic term of phi in our model that we interpret as a metric living on this space. And I won't show you, I'll spare you the details, but you know, in general, this is going to be the second derivative of our prepotential. You know, like the Hessian of it, and we're taking specifically the imaginary part. So this is going to be this is going to give us a metric on moduli space. And in particular, focusing to the rank 1 case. Okay, yeah, so this is phi that I'm using here. I'm thinking of phi in this sense. Notice how I'm using the formula for F acting on specifically the chiral fields, right? The supersymmetric fields, just the supersymmetric fields, not anything else like that. But the thing is, we can use this trick of thinking of A as a coordinate we can take out the A part of this function and turn this from an abstract matrix living in I don't know where to actually a function living on M. Right, we're taking the part of F that lives on A, which you're thinking of as a coordinate of the moduli space. So now suddenly F isn't just an abstract function we used in our action. Now F is actually a holomorphic function on our moduli space. And we can take this holomorphic function and we can take its derivatives, and that will give us a metric. And this is actually, it's a Kähler metric too. And the Kähler potential of the metric, it's this real value function that generates it, is this, it's this value here. I write this down because scrolling up a little bit, it's exactly this term, right? So physicists talk about Kähler potentials a lot because they interpret this sort of scalar value term in their supersymmetric Lagrangians as a Kähler potential on a moduli space. So this is a step that happens a lot. Okay, so you get a Kähler metric. It's not just any Kähler metric, it's a special one. It's a really special one. And the reason is because we can take advantage of duality some more and the structure of n equal to supersymmetry to sort of turn A into a dual coordinate. So I'm a little bit unclear about how this works in a sensible way, but we can think about A in a different way. We can think about A as coming from the central charge. So the central charge, remember, it was a homomorphism of the lattice to C. It took a lattice vector and it turned it into a complex number. So what I'm going to do is I'm going to define a basis of my lattice, just arbitrarily choose one. And in particular, I'm going to make it a symplectic basis because I want to keep the symplectic structure. Yeah, so this choosing a symplectic basis basically lets us define what we actually mean by the number of electric and magnetic charges. We're talking about the electric and magnetic charges with respect to this basis. And we define the two coordinates, these two functions, as functions of U. Remember, U is the true coordinate on the moduli space. A is not a true coordinate. A is like a local coordinate that we kind of pretend is a coordinate. That's not really a coordinate. Globally, U is the coordinate. And we take A to be just the central charge will probably apply to the first basis vector. And the dual, A dual, is another holomorphic function, which is Z applied to the second vector. And from duality, basically A comes from this chiral multiplet. A dual comes from this dual chiral multiplet, which we can see if we try to actually do out the duality in terms of the Lagrangian. And then when we sort of introduce this dual curvature, we need to introduce a Lagrange multiplier term, which ends up functioning as the chiral superfield for this dual basis, right? So it's like a different way of looking at this this original chiral multiplet. Sorry, yeah, chiral multiplet. So right? We have A and A dual, which are related by duality, and that makes sense because the duality is a thing that acts on charges. Duality sends like the electric charges to magnetic charges, and if I send electric to magnetic charges and vice versa, then what I'm doing is I'm swapping A and B, which is swapping A and A dual. So sort of duality is like something that plays very nice with these coordinates. And in particular, in n=2 theory, you know, by the structure of this Lagrange multiplier, you can see that the Lagrange multiplier has to be this this dual chiral field has to be the derivative of the superpotential, essentially. But again, this is for this full chiral multiplet, but we only care about the Higgs part, this like only one little part, the scalar part. So we can kind of just chop off everything else and turn this into a statement about these functions. Remember, we're thinking about these as functions on the moduli space, where the dual function is the derivative of f with respect to prepotential. And in general, you can get any number, if we want to do this in higher rank, we're going to get a bunch of functions, where we have like a list of, I guess in rank n, we're going to have n holomorphic functions, which are original A, and we can convert those to dual coordinates. So it's a different perspective on the same thing, and they have a very cool name because they're called the special coordinates, because they're really special. In particular, the symplectic form or the Kähler form on the base is very naturally represented in terms of just A and A dual. In particular, these are holomorphic functions. If you just take the real part, then wedge them together, that's going to be the Kähler potential. What's special about A and A dual is that they're kind of flat. They don't, I didn't describe this particularly well, but like, this is part of the field of special Kähler geometry. And there's a bunch of different equivalent conditions for these things to be special. But basically, we can think about these as being like flat coordinates. So they're flat Darboux coordinates. That's how we should think about A and A dual. And also notice that, maybe I'll write this down. Remember tau, the thing we care about, this parameter of the lattice, we're trying to figure out what the lattice does over space. Tau is equal to f over a squared. But remember, we have this relation here, so we can represent tau as the derivative of these two dual coordinates with respect to each other. Now, here's the thing. F is holomorphic. Remember, we are interpreting f as a holomorphic function on the moduli space, but tau was the lattice parameter. And we're expressing tau as a function of this holomorphic thing. So that automatically tells us two things. One, this BPS charge lattice, the charge lattice of BPS states varies holomorphically along the base. And two, if we figure out what it does, then we can that just tells us what f does. And that will hence tell us what the effective Lagrangian does. So we've reduced the question to asking about this charge lattice and how it varies over the moduli space. So take a breath here. Let's have a little bit of a pit stop and take careful note of what we used and what we got so far. So there's sort of three main insights from the physical perspective. We had electric magnetic duality, which sort of gave us an SL2R action on the space of, I didn't explain it in this way, but it gave us an SL2R action on the space of charges, I guess, and on the fields. But then we used the fact that the BPS states at the free limit were quantized, and then used our deformation inside to realize that they are still indeed quantized. So this looking at BPS states actually reduces us from the full real case to specifically the integer case. And this will give us a lattice. Instead of just like a vector bundle, it'll give us a lattice, but we can get the vector bundle back by just tensoring it with R or something, right? So basically we use these two properties and we got out this structure on the Coloumb branch, which is a lattice living in a vector bundle over the moduli space with some symplectic pairing. And then lastly, we use this holomorphicity, which is a very general property of n equal 2, and you use it all the time in supersymmetry to deduce exact stuff. We use holomorphicity to say that this lattice is indeed holomorphic. So these three sort of main physical ideas gave us this geometry of the Coulomb branch. Particularly, we have a special Kähler geometry on the base that I described up here. But over that, we're going to have a bunch of lattices that live in a vector bundle that also have a pairing, which we can think of as a polarization. So that's where we stand. Again, I'm going to take a breath. If anybody has questions now. Okay. So now this is sort of where Seiberg-Witten theory comes into its own. Because mathematically, we notice with this structure here, we're thinking about these as lattices. I wrote this in general, but they're specifically lattices living in R2, or which we're considering as C if we want. And instead of looking at the lattice, why don't we just look at C mod the lattice? Right? It's sort of a dual perspective on things. So that will give us a one-dimensional Riemann surface. And this Riemann surface is actually really useful. So in general, what we're doing is we're trying to interpret these lattices that we got as the integer homology of some Riemann surface, right? And that's the Seiberg-Witten curve. And this is natural because we know that homology automatically comes with this symplectic pairing. That's the intersection number. So to see this correspondence, we have a lattice up here, right? Where there's these two bases. I gave it a symplectic pairing that sort of split it into these two directions. And if I wrap it up, each of these directions corresponds to a cycle on my torus. And these cycles have an intersection number of 1 that corresponds to their pairing. So essentially, we're going to get a 1D torus on our, for every point on our moduli space. Remember, every point has a lattice. We're thinking of that lattice as a torus. These tori glue together, and they give you not just a single torus, but like a whole bunch of tori. It's called an elliptic surface. So we sort of have this vibration structure of a bunch of tori sitting over this flat plane. So this flat plane is the U plane, and the tori are generated from the charge lattices of your associated system. Now, these elliptic surfaces, okay, we're also using the holomorphicity in a very required way, because that's required to make these elliptic surfaces actually amenable to complex Sinet geometry and to algebraic geometry and all of that stuff. Fun fact about elliptic surfaces, and this, maybe you believe this because it's a thing that happens a lot with holomorphicity, but there was a bunch of singular fibers where stuff breaks down. That's sort of an inevitability of the case, but that's where all the interesting stuff happens. And around these singular fibers, you're going to get monodromy. And the elliptic surfaces are entirely determined by this monodromy. So let's look at this monodromy a bit more carefully. So let's start with the lattice. Let's start with the elliptic curve perspective. I'm imagining, let's try a intuition by balloon animals, okay? So imagine you had a balloon, like a balloon animal shaped in a torus, right? One of those like long stringy balloons full of air in a torus shape. And I'm imagining, okay, if I go around, I have a bunch of these balloons and they all are slightly twisted from one another, such that as I go around, you get a full twist in this family. And then the question is, what happens if I try to extend that to the center? What goes wrong? And you can imagine your balloon animal, what you're doing is you're taking it and you're just twisting it. You're applying the twist, you're twisting the balloon. And what that does is it sort of wraps it down into, from like a straight balloon, it sort of pinches off a little section, right? So that tells you that you actually develop a node. So this is a correspondence. Basically, if I know what the monodromy looks like, if it's just one of these little twists, my central fiber, there's going to be a single central fiber whose topology is determined by this. It will be a nodal curve. And on the level of lattices, this is perhaps more useful for the actual thing we care about, which is these charge lattices. We can think about this monodromy. This curve, what we're doing is we're shearing stuff. So as I go along, what I'm doing is I'm slowly shearing the lattice to the right as I go around. And as I go around the full loop, I sheared to the right a whole unit. So I ended up getting, I acted on it by this matrix function of SL2R, right? And I just sheared it over by one unit and I got an equivalent lattice. So that's the monodromy. And at the center, what this says is that you're going to get a degenerate lattice. That's what this nodal curve corresponds to. And in this degenerate lattice, basically you resolve things by saying, actually moving over by one unit to the right doesn't do anything because there is no right? Like the distance you move to the right gets smaller and smaller and smaller as you go to the center. What you're doing is you're sort of shrinking the lattice in this direction, and it degenerates to eventually just being a line. So we can see that this degenerate lattice, what this corresponds to, let's think about this degeneration as a, what should I say? As a charge lattice. Right, so these are the central charges. Now, if it degenerates, that means that this cycle here that I had, that corresponds to this unit, that cycle is going to have a value that goes to 0. It's going to have a central charge of 0. And in particular, the corresponding BPS state will also have a central charge of 0. Sorry, BPS state has a mass equal to the central charge, which in this case is 0. So at a singular fiber, you get singularities when BPS states become massless. And that's kind of an issue because when you have a new massless state, that means that this low energy approximation we had over here, where we assumed all of the BPS states didn't contribute because they're all integrated out and we got this nice trivial U1 theory, that doesn't work anymore. We don't get this nice theory. Instead, we need to couple this theory to these new particles that we have in this limit, these new massless monopoles. So we're going to get a different equation. It's harder to analyze, and I'm not sure about this, but I'm pretty sure this is the Seiberg-Witten equations. So this is where Seiberg-Witten equations come from physically, is they're trying to deal with these extra massless BPS states and incorporating them into the spectrum. Right, so this is a very general phenomena. This relationship between lattices and how they degenerate and these nodal curves. There's a very nice Kodaira classification theorem, which says that the monodromy is exactly determined by the shape of these singular fibers. And moreover, it has a very nice ADE classification. So that's cute, but not worth going into. Okay. So this gives us the Seiberg-Witten curves. Let's see. We're thinking about Seiberg-Witten curves as parameterizing the BPS charge lattice, and you're giving every point on the moduli space its own curve. So since we're doing elliptic curves in this case, we can write that down nicely. We have this cubic form where we can move the poles to -1 and 1 and infinity. And then we just have to determine the last pole. And that last pole is what controls the shape of the elliptic curve. Now let's look at the geometry of these things a little bit. Right. So let's not say that. The idea is we want to use this elliptic curve to figure out the central charge. The central charge is a homomorphism from the lattice to C. So what we're looking for is essentially a way to take any lattice vector, which you're thinking of as an element of the homology, and send it to a number. And there is a very natural way to do that, which is using, oops, this should be C. Sure. a very natural way to do that, which is using a differential form, a closed differential form, an element of the homology, of the cohomology. And then basically we get the central charge by integrating this differential form over this, over our loop in question. And once again, as I said before, we find a basis of our lattice. In this case, this corresponds to a homology basis, right? It corresponds to two loops that intersect nicely, like probably the obvious ones. And then this gives us our two coordinates on the base, right? Because we're defining the central charge by its action on these loops. And we're looking at the coordinates of the base in terms of the periods of the Seiberg-Witten form with respect to these coordinates. But luckily, tau, our lattice parameter, we have a Dunner expression for it. So we were trying to figure out what the Seiberg-Witten form should be. But we know that the lattice parameter of an elliptic curve is the periods of a holomorphic form. This Seiberg-Witten form is not holomorphic, it's any closed form, but specifically a holomorphic form. The ratio of the periods gives us an elliptic curve parameter, and from before, we're thinking of that elliptic curve parameter as the derivative of one of these periods with respect to the other. Now, like maybe we just want to equate these things, right? And say, oh, that doesn't make any sense. Let's ignore that. So we want to turn this into a ratio of things instead of a derivative. So we can actually turn it into a ratio of derivatives. Just take each of their derivatives with respect to the underlying coordinate, global coordinate on our moduli space, U. And now since we have a ratio of things and we have a ratio of things over here, we can just set them equal. Right, so pulling this derivative into the integral, we're looking at basically relating these two guys here, right? And this tells us that we want to choose a Seiberg-Witten form whose derivative gives us the holomorphic one form. So that what I'm saying is it's a holomorphic form on the base whose derivatives naturally give you this form. And in higher ranks, basically, you can generalize this. It's a little bit more involved, but basically what we're saying is that every direction on the base, we can get every holomorphic form. So in a higher rank, that corresponds to a higher genus Riemann surface. So there's more holomorphic forms. Well, what we're saying is we can get every single one of them by varying the Seiberg-Witten form with respect to the base. This determines the Seiberg-Witten form. And it's the Seiberg-Witten form that actually lets us get these special Kähler parameters. That's the power of it. And there's a canonical way to define the Seiberg-Witten form in terms of spectral curves that I'm going to skip for now. Because with all of this geometry in mind, let me remind you of the story so far. Basically, from all of this physics input, we learned about some nice geometry on the Coloumb branch given by a bunch of holomorphic lattices with a nice symplectic pairing, which we then realized as homology of a Riemann surface. But we also know that determining this lattice exactly determines the prepotential. So the question is, how do we determine the lattice? And as I said before, we just need to find the monodromies. And these monodromies, well, again, sparing you the details a little bit, we're going to use, it's kind of an ad hoc method in Seiberg-Witten's original paper. They sort of assume, first off, they figured out the monodromy at infinity, which you can do because you have its asymptotic freedom. You know exactly what the prepotential does at infinity. And that this is like the beta function here. And this basically just differentiating it and looking at what you get. We have this log term. This log term gives us a monodromy, a non-trivial monodromy. And we end up getting this statement where the dual coordinates swap into each other. So we interpret that as saying an electric charge, two magnetic charges mixed with an electric charge or something. Seiberg-Witten then suggests that there are two other singular points, only two. And these are, unfortunately, these are harder to deal with because they're weakly coupled, so they don't have the nice freedom. But again, we can switch to a duality base. We can use duality to turn them into strongly coupled things, right? And then we can use these asymptotic freedom. I think that's the idea. So basically, you can figure out without too much trouble the monodromies around these guys, and essentially they're conjugate to this. Yeah. So here is the structure of the Seiberg-Witten moduli space. We have the U-plane here. It's everywhere a torus vibration except for two singular points at plus or minus infinity, where you get singular fibers and monodromies around them. So in the last 2 minutes, let's kind of talk about what happened here, right? So Seiberg and Witten in this paper, they did actually like a lot of things. First off, they solved this theory, which is kind of cool, but also the methods that they use, they've sort of introduced this entire philosophy of looking at the geometry of Coulomb branches in terms of these, like these associated essentially integrable systems. I guess I'll get into that next time, that these are integrable systems over a base. And this gives us a really rich geometry to study field theories. And the other thing, and the thing I think is the most influential, is this use of BPS states. I said I would talk about BPS states, but they kind of played a minor role. But I think BPS states really, they play a very key part, even though like time-wise it's not very long, the key part of constraining it to be just integers, which actually gives you these nice tori. This is where the tori come from. And this basically introduced BPS states to the world. I mean, people knew about them before, but they didn't really use them. But now they're everywhere. They're like one of the main tools for analyzing supersymmetric field theories. So like that's kind of incredible. And basically next time I want to talk a little bit more about how BPS states are everywhere. And to say one last thing, there's a question of like the Riemann surfaces. And honestly, this notion of using Riemann surfaces, it was natural how I described it, I think, but it's kind of inspired, because to be honest, in their original paper, the Riemann surfaces were kind of incidental. Like they could have just done everything with lattices and not used Riemann surfaces at all. But somehow, at the end of the paper, they basically said, oh yeah, we can also think about them as Riemann surfaces, which either like foreshadowed or like actually prompted of like a huge range of research in modern stuff. There's a lot of present day stuff going on in this. Last thing I wanted to say was, yeah, basically in the Seiberg-Witten paper, like it's kind of funny because there's a lot of educated guesswork. And their final answer, their final reasoning for this modular space in particular was the fact that, remember how I had this formula for the spectral curve? This moduli space that you get is exactly the moduli space for this, where f of u equals u. It's like the simplest possible thing. And this describes a modular curve of level 2, and it's the universal elliptic surface over that modular curve. But it's just basically they say this is too good not to be true. And they were right, because everything, I'm pretty sure everything they said in this paper ended up being right. So that's kind of incredible. And I think that's why, maybe that's why Witten said that the Seiberg-Witten theory was the favorite thing he did, because I can sort of appreciate that a little bit more now. So I am sorry for going over time. So I will cede the floor to questions.
Thank you. That was great. Why don't I stop the recording at this point?